So we're going to start with number 5. That's what that's for. And we'll move on from there. So 5 was one of the few, if not the only one, where you didn't need a diagram because it doesn't have a before and after. This one could have been included in the website about a system, and but actually I may draw a Y in my Y. I may draw a diagram because you have a vector combination here. So what I would put in my Y here, 5. I'd probably start off with what are they? They are objects. I would say probably the 2 objects form a system. And momentum is a vector. Just to remind myself that that's true. So that means, you can also put it with dealing with momentum, direction matters, however you want to say that. Let's see. Probably be good to show that I understand that momentum is inertia in motion. Showing that I understand that while they're telling me the velocity and the inertia, I'm interested in the momentum. And this one probably would also lead me to think about that it is the momentums that combine. The common mistake will be to try to combine the velocities, come to a velocity of the system, and then figure out the momentum from that. Rather than vectorially, you need to mathematically combine the momentums. So they tell me, let's see, we got 2 objects, 1 and 2 combined have this. Object M is moving in the X direction, and M2 in the Y direction. So I'm going to draw a vector diagram just to help myself here on my house side. Actually, let's do it on my Y side. Combined momentum, is that points in a direction? 71, okay. So that would be my momentum total. Momentum 1. And momentum 2. Forming that right triangle. So if I redraw that over here now with some values, my physics equation would be momentum is inertia and velocity. So this one would be M2 V2. This one would be M1 V1. And this one is going to be I will still leave that as momentum total. Alright, so let's see, and this is the right triangle here. We know that P total squared equals M1 V1 squared plus M2 V2 squared. We know the angle in here, 17 point, nope, 71.5. And we know this is for me, 17.5 kilogram meters per second. And let's see, I know V1, the magnitude. I know V2, determine the mass of each object. So I probably don't like that equation as much now that I actually read the problem here a little bit more. So I think I'll get rid of this. That combines the two together. I'd rather deal with them separately. So I'd rather deal with things like the sine of 71.5 degrees equals opposite M2 V2 over hypotenuse, 17.5 kilogram meters per second. And that cosine of 71.5 degrees equals adjacent M1 V1 over 17.5 kilogram meters per second. And now I'm going to substitute in what I know, which will leave me with sine 71.5 degrees equals M2 times 3.24 for me, 3.24 meters per second over 17.5 kilogram meters per second. Solve that for M2. Do the same thing here down here. Cosine of 71.5 degrees equals M1 2.77 meters per second over 17.5 kilogram meters per second. So solve both of those. It's been a little while since we used the trig function, so make sure your calculator is in degrees, right? Not radians. You don't make that mistake. And that should work. Let me know if you need individual help on it. All right. So moving on to number 7. We've got the system of a man, a sled, and a rock. Why is the Earth not part of this system? Okay. Two reasons. One is that there's no friction to tie the sled to the lake. So there's no force in the direction that the momentums are. The only force on them from the Earth would be their weight, perpendicular to their motion. Therefore, it's not providing an impulse in the direction of the motion. So you have this system of the man, the rock, and the sled, and because it's frictionless, that's the only things in the system. So that's definitely where I'm going to start with my Y here for number 7. Is the man, rock, and sled are the system. And momentum is conserved in system. All right. Let's see. Is there a before and after in the problem? Yes, therefore I must do a diagram, right? So, technically I should do a couple of diagrams here because he throws it forward and then he throws it backwards, right? One way we could look at this, we could look at the impulse, but I think we'll look at conservation momentum instead. So here, my diagram, remember, if you're not as artistic as me, don't worry about it. So we have the sled, our guy, and the rock. And they all have momentum. Right. Oh. They all have momentum in that direction. Excuse me for a second while I fix the tracking. Alright, let's see if that's better tracking. Afterwards, let's see, in the first situation, we've got our man, and he throws the rock forward. So that's going to be momentum of the rock. And this will be momentum, we'll call it man and sled. And then for the second situation, we got the rock moving that way. We've got momentum of the man and sled going that way. So there's our momentum diagrams for this. Start with my one equation for this. Momentum of the system equals momentum of the system afterwards. And let's see, they're looking for the determine the speed of the sled if the man throws. Okay, so they're looking for the speed of the man and the sled. Might be good to have in here that momentum is MV. Definitely need the vector symbols. So, let's look at the first situation. In the first situation, we've got momentum total. I should have put a T here, sorry. Equals momentum of the man and the sled plus momentum of the rock. All these being vectors. Do you guys want to call to the right positive or to the left positive? To the right positive, okay. So, in both before and after, everything's moving in the positive direction, unpredicted. Of course, we get a negative answer, then it just means it's moving in the negative direction. What do they tell us? Let's see. This speed, total mass, the mass of the rock is this. And you can throw it at this. Alright, so this would be mass total, velocity total. This would be the inertia of the man and the sled is the mass total minus the inertia of the rock. Velocity of the man and sled plus inertia of the rock, velocity of the rock. So, what they tell me the mass total is 97? 97. 97 kilograms. Velocity total 0.520 meters per second equals 97 kilograms minus 0.270 kilograms times BMS, which I don't know, plus sorry, you can't really read this. 0.27 kilograms times 16.5 meters per second. Solve for the velocity of the man with the sled. Let's see. I got 0.475 meters per second. Any questions on that part A before we go on to part B? Anyone need us to pause so they can catch up, and then we'll move on to part B? We're good? All right. So for part B, really what changes is the direction of that velocity of the rock. So imagine that I wrote the top equation again, and I wrote the next equation again, and then I went right down to filling it in. So 97 kilograms, 0.520 meters per second. So momentum of the system before afterwards. We've got 97 kilograms minus 0.27 kilograms BMS. Minus now, that's the big change, 0.27 kilograms. And it's minus because that 16.5 is in the other direction. And I've just brought that out front. And what that does is increase the speed of our sled and man afterwards to 0.568 meters per second.